The act of finding them is a search process for which you need to design an algorithm. Right. Wait another 30 seconds and then we'll start.
See, now it's red.
That is just bad design. Well, or at least in a certain cultural context, red would be a warning sign. In other cultural contexts, red is sort of a complimentary thing, right? You get married in a red dress in China, so you know, like
You use red to record a lot? Like when you do a record?
Yeah, but it's also like it's a warning, right? It's like warning, a recording, you know, you are being recorded now.
I'm afraid.
Yeah. Of course, there's a whole other blue-red narrative of the constructor, which I'm not even going to touch. So. All right, Amit, would you like to say something? So you've got comments on the homework.
So I didn't grade all the questions.
Wait.
So I didn't grade all the question yet, but I grade 2, 3 questions, first question. But the thing is that I didn't see much correctness proof. Whenever you propose the algorithm, you have to prove that this is correct. So that is something to consider. And also for question 2, homework 1, question 2, nobody proved that this t function is increasing. That is the main part. That whenever you use something, try to prove it. Try to see that if it is logical.
Wasn't it enough to say that?
Yeah, so I think for that question, it's a little. I mean, I think it's acceptable to say, let's assume that TLN is increasing, but you have to at least say that, because if you don't say that, you can't even finish the rest of the proof. I think it's a little bit more tricky to sort of say, oh, for sure, you know, we can, because we don't know what the function is. I'm willing to sort of, and I don't think that's the major part of the story. I think it's okay to sort of that, but what I think what Amin is saying is that if you don't make some kind of statement about the fact that TLN is increasing, you're not actually constructing a good proof. But I'm willing to tolerate you sort of at least making that point. Right? So I think some of you are asking this about homework 2 as well. I think these points are very relevant. If you are designing an algorithm and you are not proving that the algorithm is correct, you are not designing an algorithm. You are just rambling on a street corner. Now, there may be a class called rambling on a street corner for which you can get good grades. You're not going to get those grades here. Okay? So without any statement about why what you have written down is actually going to work, that is not an answer. You will get some points. If you flail long enough, you know, somewhere in the mess of pages of stuff you write, you might actually hit accidentally a few points. That might make you happy, but it shouldn't. Because there won't be enough, you know, if you're looking for an actual grade, then you're not going to get enough points to get a good grade. But you have to be able to reason about the correctness of it. That's all we do in this class. Right? We design algorithms that are guaranteed to be correct, or that have formal guarantees of when they're correct. Right? That is the thing in this class. Right? And so you have to be able to do that. And what I've tried to do is for every kind of technique we use, explain the way the proof of correctness will work. Usually it's an induction proof for the most part, or in the case of greedy, it's more involved reasoning about optimality, which you have to do again. Right? But you have to use that structure. Right? It might be difficult, I know. It might be hard to pin it down, but you have to make the attempt. If you don't do that, you're not going to get points for it. So I don't want any of you to come back and saying, well, here's my algorithm. Why haven't I got a point? Well, is it correct? Like, well, I tried, you know. Some people even say, well, I tried it. Like, that's not good enough. It has to work all the time, which means you need to have a formal guarantee. Right? That's what we do here, and that's what I expect. Okay? All right. Okay. On that cheery note, let us move on. So we were talking about local search last time, and we were talking about this idea coming out of a greedy. So I went from greedy algorithms to local search, and maybe you know, actually, worth pointing out, local search is a greedy procedure. It's a particular kind of greedy procedure where you say, look, I look around, make some local change to my position, and then I do something if it improves my position. Right? So I do something locally. If that swap between those two people who got the gifts works, I make it because it locally improves my position. And of course, we know that in general this may not give you the optimal solution, but you hope it does because you're doing this always try to get better strategy. Right? So if you think more broadly, right, under what conditions would it be the case that this strategy actually gets you to an optimal solution? Right? So if I'm giving you a technique, I'm saying use this technique, and you want to say, okay, for what kinds of problems am I guaranteed to get a globally optimal solution? So that gets you to sort of a much larger question that greedy algorithms or local search is only one small piece. This is sort of this general problem of function optimization. And in particular, the continuous variant of local search, which is called gradient descent. Again, like I said, gradient descent and its sort of relatives, things like stochastic gradient descent, are the tool of use right now in pretty much all of machine learning. So just from a point of view of this is a very powerful technique, you should understand how it works. You should understand why we think it's a good tool to use. And you should understand the limits of the tool as well. So let's think about the following problem. So to start, we won't go to gradient descent directly, because that's really a solution. Let's first ask ourselves, what is the problem we're trying to solve? And the usual problem you're trying to solve is you have some domain. So I have some kind of domain. We'll call this D. And you have some function that's defined on D and maps to the reals. Okay? So you give this sort of function topic. And the goal is find x star such that so just a fancy way of saying find the point that minimizes the function. So maybe that point is somewhere here. Okay. All of optimization can be put into this framework, which also means it's a very general framework. It's not a very useful framework. It's so general. Right? D can be arbitrary. D can be defined by a bunch of constraints, or it can be unconstrained. It could be anything. So almost any problem you think of can be put into this kind of framework. Maximization, minimization, what have you. And so one set of tools that local search represents is the idea that, maybe I'll start somewhere. Let's say here. And I want to get to X star somehow. So I use local operations to kind of wiggle my way around, do something. Maybe if I get lucky enough, I eventually end up here. When I say I mean the algorithm starts at that point, it makes some local change to the point and it moves a little bit. It makes another local change and moves a little bit more. And eventually, hopefully, it gets to where it needs to go. Okay? So this is a broad kind of class of strategies. You can think of like a search strategy or whatever you want. It's a way of finding that optimal point. And so one obvious strategy to apply is, well, start from where I am. And if I can improve my situation, move. Right? So I might say, so one way to think about this is that pictorially, I start off at this point, I draw some kind of neighborhood around myself. Okay? A small neighborhood. And I say, okay, in this neighborhood, where can I get to that is better than where I am? Think of this as saying that I'm standing here, I'm on a hike and trying to get down to the base. I look around me and say, okay, which way can I go that will get me going down? And I see a bunch of different choices. I pick one of them, and I go and it gets me further down. Right? So you're starting at some point X. Right? So you start at some points to start at X. So let's say X0 is the starting point. Find Y in a ball of some radius around X such that f of Y is equal to, is less than f of X0. Okay? And then set X1 to Y, and then, right? So this R, the radius of the ball, is the amount of locality you're incorporating. Suppose I make R infinity. This is the original problem. Like find a point that is, well, it's not, oh, sorry, it's not. It's just it's finding any point that's better, right? So I can make R big or small or whatever. The bigger I make R, the more choices I'll have. The smaller I make R, the fewer choices I'll have. That's the locality of the search. And all it's saying is, look, just improve. That's the greedy step. Just improve a little bit. Okay? And then keep going. Now, can you imagine a condition under which this will not work? What could your shape of your function look like? I don't want a quantitative answer. I just want a visual answer. When could this fail?
That the minimums are outside of the radius, and the circle is all filled with f of x greater than x1.
So in other words, you're worried about a situation, and we'll try and draw this in 2D, where, so let's say a failure. Your landscape, and you think of this as a slice in 2D, looks something like this. Right? Your x is here, and your radius of interest is basically, let's say, from here to here. And now the problem is, there is no y in that ball of radius r, such that f of y is less than f of x0. And so I will get stuck. There's a name for a point like that. You know what it's called? It's called a local minimum. And that's true. These methods I'm describing to you will only find local minimum ever. They can never be guaranteed to find a local minimum, except under certain conditions. One condition is if all local minima are also global minima. Right? That's one condition. So for example, if your function looks like this, like a sine wave or something, then yes, I got stuck in one local minimum, but I don't care because the value I got is the same as at the other local minimum. This is a case where there are multiple optimal solutions. I happen to find one. I didn't find another, but whatever, it's fine. So that's one picture. Another picture is the same kind of picture where all local minima are global minima. There's only one. And so it looks something like this. Right? Now I didn't draw this quite right, but a more formal version of the second example is when your function f so how many of you know what a convex function is? Some of you? Few of you? Okay. So roughly speaking, informally, a convex function looks like a ball. Right? More formally, a convex function is a function. So f is convex if for all x and y the value at the mean is less than equal to the mean of the values. So what does this look like pictorially? Pictorially, what it looks like is this. If I draw my function out, and let's mark out, let's say, x here and y here, okay? F of x plus f of y divided by 2 would be roughly, oh sorry, what did I didn't do this right, sorry, let me do this wrong. x is here, y is here. So this goes up somewhere here, this goes up somewhere here. Okay. So this is f of x, this is f of y. F of x plus f of y divided by 2 is the midpoint of these two things. It's that height. Right? But what is f of x plus y over 2? Well, there you just look at the midpoint of those two things. Maybe that point is somewhere here. This is x plus y over 2. And this is f of x plus y over 2. So now we're looking at this point versus this point. So one way of thinking about convexity is that if you draw a line across from 2 points, that's always above this function below it. The concave function is the opposite. Right? The line is always below the function. Okay, that's why I said the convex looks like a bowl. So the simplest convex function you can probably think of is the parabola, like y is equal to x squared. That's convex. So why do you think that for a convex function that descent procedure will work? Intuitively, at least, it should work because you always get to go down, and once you get to the bottom, that's where you need to be. Right? There's no other way to go. Right? You're never going to get a situation like this because this function is not convex. Why is this function not convex? This function is not convex because if I took this point here, that point there, and I connected them up, the mean value is below the function mean. So that part is not convex. And I think that has to be true for all pairs of points. So that function is not convex, which is why you had to go up to get back down. But if function is convex, you're always going down. So intuitively, that makes sense. But you can prove this, right? So you can say, you can actually show that you can guarantee that the procedure I described will always get you to the right answer for a convex function. Why? Because if you think about, so just draw a convex function again, right? And I'm at some point x, some point x here, right? This is f of x, and this is x star here. The optimal solution is f of x star, right? What do we know? We know that if we draw the straight line, right, from here to here, and we take some point in the neighborhood of y that is nearby x. So let's take any point here. Let's call this y, which is any point you want to see. What we know, so any point in y that is on the path from x to x star. So this is a point we would like to get close to, right? All we need to do is make sure that f of y is less than f of x. Because if we do, then y is an eligible point to advance to, and we can advance to it. So y is a good point, right? Y gets us closer to x star. We would like to move to y. We don't know if we can, but our rule said, see in the radius around you and see if there's a point whose value is less than yours. So now what's the value of this? Well, we know that f of y right? So let's say y can be written as lambda times x plus 1 minus lambda times x star. Okay? It's some kind of interpolation between x and x star on the x-axis there. So then we know that because of convexity, and this is the point, f of y is less than or equal to lambda f of x plus 1 minus lambda f of x star. This is the generalization of what I wrote on earlier. Instead of half and half, I have an arbitrary lambda and 1 minus lambda. Okay. But this is a convex combination of f of x and f of x star. We know that f of x star is less than or equal to f of x. So it's like saying, look, I wanted f of x. I've taken out some of it and replaced it by f of x star, a lambda amount of it. But f of x star is less than f of x. So this quantity has to be less than equal to f of x. And therefore f of y is less than f of x, and you will make progress. Okay, so all we need is convexity to argue that there's always a way forward. And that's the key, right? You want to be able to say, look, there's always a way to make progress. You'll always find that path down. Like, you may not like it, maybe very steep, it may be full of rubble, but okay, it's a path down. Okay. So as long as your function is convex, the procedure I described above is guaranteed to work. Yeah.
So like, what if this x is at the maxima and you have two choices to descend down, both are equal? So like,
The two choices depend on why.
so like, for example,
What does my function look like?
like this, and you are at the top.
Is that function convex?
Not convex, but like, oh, okay, so.
Sorry, store's close to the day. Once you say not convex, I can't talk to you. Okay. That's the point. That won't happen. Exactly. The function has to be convex. In particular, it has to be convex over the domain you're looking at. Maybe you're looking at over the positive reals. If the function does crazy stuff in the negative reals, I don't care. But if I'm saying over the positive reals, what the function looks like, it has to be convex. Okay. So for convex functions, this local search descent approach works. But you know, what is very unsatisfying about this is that you have no way of telling how long it's going to take. Right? If I choose my ball, so what are the various problems? Right? Suppose I choose my ball to be too small. So what's going to happen? If I choose my ball to be too small, then what's going to happen is that, so let's draw this again. So I start here, I might move down 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 here. I mean, I'll eventually get there. It'll take a long time. Right? Suppose R what'll happen now? Sorry? Well, I don't know about never. It will eventually, but it might go like this. Right? And again, it's kind of hard to reason about what's going to happen. It might decide to jump across. Again, I'm not saying it will do this, but it could. So, choosing R is kind of tricky. Also, and does it show up in this picture, knowing where to go is also tricky. Right? If you think of this not just in 1D, but this, basically it's up and down, it's like a 2D thing. Where do I go? There's all these choices. There's a whole infinity of choices I could make. Right? And so, we won't actually answer the first question. That whole first question of how you choose, what R you choose, is like a study of the whole field of optimization. We won't touch on that. But we will address the second point of how do you decide where. And that's where we get to gradients. So this is where you need to sort of refresh your memory, if you have a memory to refresh that is, what sort of multivariate calculus, right? So, how many of you know what the grad of a function is? Some of you do? So okay, how many of you know what this means? Okay, that works out, right? Okay, so this is just the multi-dimensional version of the first one. So clearly it's the same thing, it's easy to know. So generally speaking, if you have a function f of x, right? You can write this as it's a vector. It's a vector that therefore it's a direction. And formally you write it as basically a set of coordinates where you do partial derivatives with respect to each coordinate. If it's an n dimensional function. Right, so if there's just one variable, of course it becomes the first one, but in general it could be more. So for example, if your function is a parabola, so z is equal to x squared plus y squared, right? The gradient at any point, so the gradient, so let's say f of xy is equal to z, then grad of f is equal to, so the del by del x will be 2x comma 2y. Right? Okay? Yes? Now this is a vector. And the vector at the point xy, which says 2x, 2y, is basically a vector from the origin going right through xy. And has double the magnitude. So, so for example, if I were to draw in the plane, what might things look like? At any point xy, this would be what the gradient would look like. If I had a point here, the gradient would look like this. If I had a point here, the gradient would look like this. Like a vector so on. If you now imagine what the parabola looks like, right? If you look at it from the top and kind of cut it in slices, it kind of looks like this, right? So, I'm very bad at drawing circles. Okay. So these are what the contour lines of the, if you think of slicing at fixed z values, this is what the contour lines of the parabola look like. And what you notice is that those arrows, they're pointing in the direction of the increase of the function. Do you see that? Because think of the function sort of growing out like this. When you're looking at slices, they're always pointing out, which is kind of along the direction of increase. Okay? Which means that the opposite of the gradient is actually a direction of fast descent. So if you look at the gradient of a function at any point and you take its negative, that direction is a direction which is decreasing most rapidly. Like if I think of this function here, along this line, by definition it's not decreasing at all, it's constant. As you kind of move in this direction, it starts increasing slowly. If you go this way, this is the quickest way to get to the next contour line. Similarly, this is the quickest way to get to the previous contour line. So it's descending as quickly as possible. Right? It's normal to that line. So the gradient is always normal to the constants. So it's perpendicular to it, which means it's the fastest way to get back to the previous contour line. So the negative of the gradient is the steepest way down. So if you're, again, on your hike and you're looking around, and this is exactly not what you do on a hike, but you find, oh, well, maybe, okay, you're skiing, and what you want to do is find the steepest way down, because that's the funnest way to go down. You look around, it's like, oh, there's the cliff. You go down that way. Right? So all of this is a fancy way of saying that the gradient, the negative of the gradient, is the direction of steepest descent. Okay? And so you can now use this to build a local search procedure along the lines of what I just told you. So I start off with some point x0. So x0 is equal to the starting point. Okay? And I now want to get a new point. So I'm going to say that, repeat xi is xi minus 1 plus an update with respect to the gradient. But the gradient is going to be negated, so it's going to look like this. Grad f at xi minus 1 times a little factor. Say how much do you want to move that direction? Right? Till xi minus xi minus 1 is less than equal to 0. So till you stop making progress, essentially. If your update is pretty close to the previous one, there's nothing else to do. Another way of thinking about this is what happens as you get down to the basin of convex function. What happens to your slope? It goes to 0, right? Once you hit that, you're at 0. So if this was 0, you would have no change. If you're actually at the minimum, you would basically see no change at all, which is what you're trying to capture. So what is this term doing? This is basically saying how much do I want to move? Right? The larger this gamma I is, the more I'm willing to move in that direction, the more aggressive I am. It's not quite behaving like R, but it kind of is. You're saying how much am I willing to go. And this, in its full generality, is what gradient descent is. People say gradient descent is what. This is what is called a first order method. First order because it's using the first derivative of the function. There are what I call second order methods, Newton's method, that use the second derivative, which in this case is called the Hessian, which we won't get into right now. They usually are faster. This is slower, but we haven't talked about time yet. Get a question?
For the condition to stop, not less than x slow.
Yeah, you pick some tolerance.
Yeah, but instead of using the value for x, can I use the value for h of xi? This is more accurate.
Oh, that's a good point, actually. That's a very good point. And yes, that might actually be a better thing to do. You could say, I'm not worried about the point converging, I want to see the value converges. So you could do that too. I have to remember now which is the one that is preferred. I've seen both.
Because some cases, even I have the small distance between x and xi minus 1.
Yeah.
But the value is still very big.
Well, yeah, so technically you could set epsilon to be f inverse of whatever value you want as a tolerance. So it really depends on what you want, right? Do you want to get tolerance in the optimal value, or you want to get something that sort of converges? You could do it either way. I think it doesn't change the argument. So if you like, you can replace this by f of x minus f of x minus 1. Less than equal to some. Or you can even use both of them. So this is gradient descent. And because if we assume that f is convex, this will give you the optimal solution. So for a lot of problems, you want to solve convex optimization. It's a general problem. You don't know much about the structure of the problem. You can't apply some specific greedy algorithm. You just run this, and it will give you the answer. So gradient descent is very powerful because it's so general. It doesn't need to know anything about the function you're optimizing except that it's convex. It also needs to be able to compute a gradient, which is often an issue. So again, in deep learning, often there are all these techniques to compute gradients automatically in the network because you need that kind of thing. Sometimes that can be expensive as well, but that just is what it is. Okay. Right.
Here for choosing x minus 1, we have to examine all the points.
Why? X minus 1 is a point from the previous iteration.
Okay, okay, fine.
Okay. So so to be more specific, you know. And then, or maybe for here. So the I is basically representing the current time step. In the current iterative step, use the previous iterative value. So you create a sequence of values. That make sense? Any question? So again, in an algorithms class, we tend to avoid often talking about continuous optimization for various reasons. But I just want to point out that to connect what we've learned about greedy algorithm local search to a very, very powerful and commonly used framework for continuous optimization, which is gradient descent, which, as you'll see, has all the same questions that came up when you were looking at local search. Remember, we had two questions in local search. First of all, does it stop at the right answer, and how long does it take? So we've argued that it will stop at the right answer because it's convex. The question of how long it takes is a much more complicated question. And for gradient descent, in fact, it is very hard to give good guarantees on this in general. For a convex function, you can show that it converges at a certain rate, but it can be quite slow. And in fact, there are, I'll link to the Wikipedia page for gradient descent. There's some very cute examples where the function is such that the gradient descent goes kind of zigzag like crazy before it gets the right answer. And it seems totally dumb, but that's just because the gradient looks like that. It can't help it. So gradient descent can actually can do quite poorly. So in terms of how long it takes, but it is very simple. So that's the attraction and also the downside. Okay. What I wanted to tell you about also was stochastic gradient descent, because it's just a slight modification of this. And again, it makes sense in a machine learning context. I won't go into that detail, but it works for certain kinds of functions. Okay, so let me explain what I'm doing. So one of the problems with gradient descent is that at every step, you have to compute the gradient. Okay. Now, if you have a closed form function, you can write down the gradient once and you can do this, it's not a problem. But oftentimes, the function you're optimizing is some kind of function of your data. So in machine learning, often what you're saying is that I have some kind of model, and I build a model and I evaluate it on my training data, and I look at the error my model gets on my training data, and then based on that, I might update my model. So the typical function you might see, so your function is a function of the parameters of your model. So if you don't like thinking about machine learning and parameters, you can just think of, I'm trying to find a straight line, and a straight line in d dimensions has d plus 1 parameters. So this is a function of those d plus 1 parameters. I'm searching over all possible straight lines that separate a class of points, right? So there's d plus 1 parameters there. And so that's your vector of d plus 1 parameters is theta, okay? And this is usually written as some sum over I is equal to 1 to n, some loss function, which takes the parameters of your thing and some point. Which is basically saying, look at the error of my classifier at that point, and the next point, the next point, the next point, the next point. So if you have to compute the gradient of this function with respect to theta, right? So we have to be really careful now, because I'm using, maybe I should use the term xi, because I'll just confuse things. We just call it pi or something, the ith point. Okay. So now I have to compute the gradient of this function. I have to compute the gradient with respect to the parameters theta, which is of course going to be sigma I is equal to 1 to n. Right, pi is a constant here. Theta is a variable, and I'm going to differentiate with respect to that. Which means that if you think of your, if you have a training set, there's a million points in it. Every time you have to do the gradient, you have to evaluate the sum over all n points. And that's kind of expensive, right? So one trick is to say, look, I am not going to evaluate the gradient along every single point for every single evaluation of my data. I'm just going to pick one of them. So instead of actually computing the gradient f of theta, I compute this approximate gradient. Okay, and I use that in my next iteration. When the next iteration comes, again I have to find the gradient. I don't want to compute it. I pick a different I, a different point, and I do it again. And the trick is I pick these points at random. So I choose an I at random. Okay. So in other words, if I looked at my gradient descent procedure, okay, what I'm going to do now is I'm going to replace this by so maybe I'll write it this way. This is my starting value. Okay. And now here, To evaluate this, I pick data at random each time. That's where the word stochastic comes from. So this gradient descent, the stochastic gradient descent, or SGD as everyone calls it, is where you do this modification where you pick a point at random to evaluate the gradient. Okay. And it turns out that what this does is, of course, it makes the evaluation of the gradient way faster. Right? Instead of summing up over n things, where n could be 1,000,000, I'm doing 1. So I get a huge saving in running time. Of course, it's inaccurate. It's not the best way to go down. But remember, I didn't say for local search that I need the best way to go down. I just need some way to go down. Right? As long as this gets me down, I'm fine. So it might seem like it'll actually end up being slower and you'll need more steps. But that gets counterweighted by the fact that each step is so much cheaper. So in any of these iterative processes, there's two things, right? How long does each iteration take? And how many iterations do you have? Gradient descent has some number of iterations, and each iteration is very bulky. Here we're saying, well, you're going to have probably more iterations, but each iteration is way faster, and so the product of the two still works out to be faster. And that's basically why everyone uses stochastic gradient descent for these kind of problems. It still has the same issues as gradient descent. You still have issues with guarantees, but there's a bunch of nice work that's been coming out now over the past 10, 15, even 20 years, sort of analyzing stochastic gradient descent and showing how fast it converges. So for iterative procedures, you ask questions like, how fast does it converge to a single point? You can't say how fast does it get the optimal solution because there may not be one if it's a multi-thing. What you're saying is how fast do you get to a local minimum of some kind. And so the convergence rate basically says, how many bits of precision do you get on where you need to get to. And so it's a different way of talking about the same running time kind of issue. But because it's iterative and it sort of always gets just closer and closer and closer, you're not so much saying how many steps does it take, but how quickly do I get there? Okay. So stochastic gradient descent has reasonable convergence rates. I'm not, off the top of my head, I don't remember what the convergence rates are. This is an ongoing area of study right now in machine learning where people start to study how fast these things work. And gradient descent also under certain conditions. And there are other, like I said, Newton's method, and sort of this what is called the LBGFS method for non-convex optimization. There's a whole slew of things, and like I said, you could do a whole PhD on optimization, studying all these different methods. So I won't go into that here. But I just wanted to sort of spend some time telling you about this continuous mode of optimization that is basically a local search procedure. So local search is actually very, very widely used and compelling because, and the main attraction is that it's simple. It's universal. You can apply it to an arbitrary function. This will work even on a non-convex function. You just will get some local minimum. And that's what happens in deep learning. You get some local minimum, and that's fine. So that's all you can hope for. And that's why we use it. But again, keep in mind that it has limitations. You don't know how long it's going to take to converge. You don't know if it'll converge the right answer unless it's convex, and even then there are issues. Yeah.
So theta here is
the parameters of your, say, classifier. It's the thing you're optimizing. So when you're optimizing, when you're trying to learn a model, your function is a function of the parameters of the model at the error you're evaluating, right? So the coefficients of your line, let's say.
It could be one of the variables that define the function f. For example, the function f is a function of n variables.
Yes.
And theta is one of the variables.
When I say theta here, I think of the whole vector. Theta is a vector. What I should have said here, to make it clearer, think of theta as a vector. So when I talk about those points moving, my point is in a high dimension space. Each point in my high dimension space is a possible answer to the problem. It's a possible classifier. And when I do gradient descent, I'm saying, okay, let me move from this point to this other point, which is another classifier, or the other point, which is another classifier. So I'm in the space of classifiers where each classifier is named by one vector. So to make this more concrete, imagine trying to construct a plane to separate red and blue points, or even a line to separate red and blue points. So let's say I have a bunch of points. This is classic linear classification. I have a bunch of points here, and I have a bunch of points here, and I want to draw a line that separates them. This is a machine learning problem, right? I want to learn a classifier to separate red and blue. Now the classifier is a line, so you can write it as ax plus by plus c equal to 0, right? Or if you like, you can write it as, y is equal to mx plus c, right? Really it has 2 parameters, not 3, because I can divide by c everywhere, as you were saying. So you can think of theta here as the vector m comma c, okay? And now my function, right? So my loss function, which is a function of m comma c, right, is basically the summation of, let's say we're doing the squared loss. We're doing, and we have a bunch of points with, I ended up doing a regression. Okay, never mind. Okay, so this will be basically, let's say my points were xi is red, so let's say red is -1 and blue is +1, right? Then what I want to say is that, and that's the label yi. So what I want to say is that, okay, someone help me here. So it will be a sine of m times xi plus c, right, times yi. Is that correct? Maybe I should square it.
Sine of y.
Sorry?
The original into the.
Oh, I'm sorry. Yeah.
The sine of the.
Right? And again, there are ways to, but this is my cost function now, and I want to optimize this function. You could do it another way. You could say that if you don't like this function because it's hard to optimize over sines, you could say mxi plus c minus yi whole squared. This is another way of saying what is the difference between the predicted value and the actual value. Oh, sorry. Is that? No, that's not right either. How do I write this as a square loss? Huh? Yeah, this is square loss, right? It's like machine learning 101. I have to mark now. No. Sorry?
This is a regression.
Yeah, I just saw a regression. I just saw a regression problem. So,
we can do a Hinge loss diagram.
okay, tell me the Hinge loss version. What is the Hinge loss version?
This is the max.
No, you just multiply the y.
I just said that's the first one.
Yeah, so mxi plus c into yi minus the 2 level.
Minus the?
The 2 level, the ground. The actual level.
No. The true level is y.
So the, oh, yeah.
Someone who took a machine learning class will fix this. Before everyone tells me they all laugh at me, so I don't want. How are you doing this? You guys remember this one? So let me think. Okay, so
Just yi minus the sine of mx
Yeah.
plus c squared.
and then square that. But that's what I wrote earlier. No, I didn't write that earlier. Okay. Yeah, that might be a better way to do it. It's not ideal, but I want to get rid of the sign. That was what I was concerned about. But okay, there's a way to do this. You have to play with some more games with the function. But okay, but you get the idea. At any rate, now that I've gone back to this digression, this function is a function of m and c. Those other things are constants, right? So the total error or the total penalty I'm paying for this classifier is this function here, which is sum over all points, right? So when I take my gradient now, I'm taking a gradient with respect to m and c. These are the variables. And so when I update, I'm going to get a new m prime and c prime, then a new m prime and c prime, and so on, so on, so on, so on. So my classifier keeps moving till it converges to the final answer. Yeah?
So my conclusion now is even when theta is a vector, then how can I define, because a vector can be defined by magnitude and also the direction, which one I can choose?
It's a vector. It's just a bunch of, no, forget magnitude direction. It's a bunch of coordinates, right? A vector is just 2 coordinates, right?
Yes.
Okay, so now let's look at the update here. This is also, oh, I forgot my gamma. That gradient there, that stochastic gradient, is also a vector. The gradient of a function is also a vector. So that's it. So I'm taking one vector and I'm updating it by another vector. That's all. It's all vectors here. There's no, I mean, you can think of magnitude direction if you want, but they're really just tuples, right? I'm just moving in space a little bit. So I take my M and C, the gradient tells me where to go, and I update to M prime and C prime. That's it. Think about it. You can come and ask me. All right. So that's all I want to say about continuous optimization. We will sort of get back to more discrete optimization till we get the linear programming. We're getting to continuous optimization. But for now, I just want, again, point is gradient descent is a local search. It's free up with all the attendant benefits of the functions. All right. We'll see you all next week.